So yeah, so some of you might have seen topology. If you go to SUMAC, the Stanford University Math Camp, they teach a course on topology. But if you haven't seen it, that's fine too. So this is just a topic that appears almost everywhere in mathematics, from places like calculus to places like number theory. It's something that's, if you go further in your mathematical studies, it appears everywhere. So I'll tell you a little bit about what topology is and how it relates to this cops and robbers problem. So yeah, here's the general outline of this talk. It's not going to be the full hour. It's probably going to be closer to 50 minutes. So first I'm going to tell you a little bit about topology. Then I'll tell you about this tool that we use to study topology. And then I'll get to this evasion path problem, or the cops and robbers problem. And then the fourth step is pretty much what people are doing nowadays at the research level at places like Stanford or UPenn or where I am, KTH, or places like, also people work on this in computer science too. So this cops and robbers problem is something that many of you have probably experienced if you even play like video games, for example. So if you play some video games and there's some sort of like stealth mission where you want to avoid detection, well, the question is, how do you avoid detection? Is it possible to avoid detection? Or, well, one of the guards you're trying to avoid, will they see you? So that's really the essence of this. And we're going to use this thing called topology to study this question. So what is topology? Well, if you ask some very theoretical mathematicians, they'll say it's the study of open sets, but that doesn't really mean anything. For me, it's really studying what properties of objects remain the same under kind of this smooth deformation, whatever that means. So the first question you can ask is, what does it mean for two objects to be the same? In topology, they study these things called homeomorphisms, but really it just means that two objects are the same if you can kind of deform them smoothly from one form to another. For example, the most canonical equivalence is this one right here, from coffee cup to donut. Or I guess coffee cup on the right and donut to the left. So you can see how in the left we have a donut, and we slowly kind of like squish the donut, the left-hand side of the donut, to form the handle of the coffee cup. So that's what's happening here. But we aren't really doing any like crazy motions. We're not like tearing the donut apart, where we're just kind of like pushing things around and stretching them. So you can see like the sequence of transformations that turn this coffee cup into a donut is just pretty much stretching this hole in the middle and like compressing until we get this actual handle of the coffee cup. And we get this kind of middle part of the coffee cup by pushing down, by like smushing. So I didn't really do anything except like push things around and stretch things around. So that's what it means for a lot of topologists for two objects to be the same. But then you might ask, well, how do you tell if things are different? That's also a very good question, and that's what the focus of a lot of topology courses are. So it's very difficult to tell when objects are the same. Like usually you need to write a function that takes this donut and outputs a coffee cup. Off the top of my head, I have no idea how to do that. And I've been doing topology for a while. But the claim is that these two objects are the same. So in general, it's very, very difficult to show that objects are the same. And for example, there are some questions that people have been asking that are pretty much reduced to how or when are two objects the same? And these questions are things that get people Fields medals, or they call it, those are like the Nobel Prizes of mathematics. So some questions there can be reduced to the question of when are two objects the same, and that's when can we deform one into the other via this type of transformation, smooth, like pushing things around. That's something that people at most universities care about. So it's very, very difficult to show things are the same. So what do people do for math research? They create tools to show when things are different. So sorry for the low quality image, but you can see, or these two shapes, the sphere on the left and this donut on the right, they're not the same topologically speaking, because I can't really get this hole through any like smooth pushing of the sphere. So imagine the left-hand side is a basketball and the right-hand side is a donut. So how do I get the hole in the donut? I can't like input my hand and push the sphere down to get this hole. So there's no way to get from the sphere to the donut without creating some sort of hole. Okay, I see a chat. Oh, Harry Ball theorem, yeah. So if you've studied vector fields, or if you've, so I see, yeah, someone said something about the Harry Ball theorem, yeah. If you study vector fields, you might have seen the Harry Ball theorem. So that there are some more sophisticated tools that people use. Okay. Yeah, so the main idea is that there is a hole for the donut, but there isn't really an equivalent hole for the sphere. Yeah, exactly. So we're not going to go with something as advanced as the Harry Ball theorem, but we're going to just deal with something called homology. And we're going to study these things called invariants. Namely, we want to study properties of objects that are the same after this kind of thing we call the homeomorphism, or pretty much topological objects that we view as the same.
So some people are asking, but what exactly counts as a smooth deformation?
Okay, a smooth deformation is something that where I don't really tear anything. I don't make any rips. So you can think about it in terms of something that is continuous. So if you've dealt with calculus before, you probably have dealt with continuous functions. Or if you haven't dealt with calculus yet, then maybe if I want to draw a line on a piece of paper, I can draw a line without lifting my pencil or pen off the paper. So I view that as a continuous function. So pretty much what I want to do is I want to kind of push things around in a similar like continuous manner. So basically I can't like make a jump. So like if I have a graph of a function and there's like a jump, I would say that's not really a smooth function. It's not even continuous. So we just don't want an equivalent of a jump for these deformations. So basically I can't really rip or like puncture my objects. So for example, I can't get this hole without making some sort of like jump. So the formal definition is, if there's for those of you who took like a set theory course, is I really want a continuous function or with a continuous inverse. So a bijective function with a continuous inverse that is continuous itself. Yes, so can you move parts of the surface through other parts? Okay, so great. There are lots of questions. Great questions. So first question says, can you move parts of the surface through other parts? So the answer is yes, you may move, you can keep pushing parts of the surface around the object. So for example, if you have like a bump on this torus, you can sort of move it to the other side. Yes, so if that's what you mean by that. What's the formal definition of a topological object like a torus? So a torus, there's some ways to define it, but people define it as a object with a hole in it. So namely, they define it as a sphere crossed with a sphere. So a product of a sphere and a sphere. So S1 cross S1 is what they define as a torus. And an n-fold product, so if you cross n spheres together, that's an n-dimensional, n-torus. Can a deformation be continuous but not smooth? Yes, it can be continuous but not smooth. Then all knots are equivalent to the unknots. So through a family of immersions, I believe that's true. But most people study knot complements.
But so this I think is asking about homeomorphism. So yeah, all knots are homeomorphic to the unknot.
Yeah.
But you're right. You should study complement.
Yeah. So most people study the complements of a knot because it's easier to study these like hole properties for the complement of a knot. Yeah. So these are all very good questions. So keep them coming. So they're very good. Well, the complement of a torus, you have to look at what space you're embedding things into. So it depends on what space you're embedding things into. But I think Simon can probably tell you more about complements of knots if he teaches an algebraic topology course or just complements in general. So complements are a very interesting field of study because there's a thing called duality that people study a lot. So there's things like they call like Alexander duality or Poincare duality that tell you about how to study complements. So again, Simon might mention this at some point in one of his courses. So we want to study properties of these objects that are the same even when we do these deformations. So in this picture right here, one property that remains constant is the number of connected components. So here I have like a connected component here, and I have this tree here that's connected, and then I have this line segment that's connected. So there are 3 connected components, and that's actually one of the topological invariants that we are going to study. So namely, it is what we call H0 of a space. So that's the number of connected components. There are 3 of them here. But the one that we're going to deal with, and one that you learn in an algebraic topology class, is the number of holes an object has. So it's hard, you will learn what a hole is if you take an algebraic topology class. There's actually a formal definition in terms of linear algebra, but we will not go into that in detail. But some intuition is a 0-dimensional hole is how many connected components there are. 1-dimensional hole corresponds to like a circle, and so on and so forth. Like a circle has a one-dimensional hole, this torus has a two-dimensional hole, so on and so forth. So pretty much we're going to use this idea of holes to study this evasion path problem. But first I want to tell you, how do you build things in topology? Well, yeah, okay, question. Yep, simplex is an n-dimensional pyramid. That is correct. An n-dimensional simplex is an n-dimensional pyramid. So basically, how do you make all these shapes? Well, you make them through kind of generalized triangles. So what do I mean by that? I mean that I can create most of my topological spaces through a combination of like gluing points, line segments, triangles, tetrahedrons, so on and so forth, gluing them together, and then kind of like deforming, stretching things, and that, or compressing things, and that'll get me my shape. So, for example, how do I get a sphere? I can take a triangle, and then I can glue everything together at the North Pole. So I can take a 2 simplex and a 0 simplex, and that gets me a basketball or a sphere, for example. So just imagine if I remove the north, just one point from the sphere, it just becomes like, a disc or a triangle or something like that. And then all I need to do is attach the points at the top, and that gives me my sphere. So it turns out that most objects that people care about can be built through gluing these kind of generalized triangles together. So if you studied, so it seems like some of you are more advanced. So people study CW complexes, if you've seen that before. And those are, and everything that most people care about is, they call it homotopy equivalent to some CW complex, for those of you who are more advanced. So what does this have to do with this evasion path problem? Okay, question. So the question is, do we glue an infinite number of simplicities together to form a smooth surface? So the answer is every finite, well, it depends on what you mean by, okay, so let me see. Okay, so to form a smooth surface, what you do is you just stretch out the like, for example, the triangle. So this triangle, you can just stretch it out a lot. And so you can just stretch it and then glue both ends together, for example. And that gets you a cylinder, and then you glue the other 2 ends together to get the donut. So for most things that we're going to deal with, we're going to deal with a finite number of simplices. So that's a good question. So most people don't actually study infinite complexes. Those gets a little bit weird because you need to form a topology there. But most people deal with a finite number of simplices. So that's a good question. Yeah. Okay. So yeah, so how does this have to relate to the robber problem? Well, you can imagine that every like security guard is one of these 0 simplices. So every security guard is a point, and this ball around them is what they can see. So basically, I'm going to look at what every single security guard can see in their field of vision or their field of view. And how am I going to make the complex, or this simplicial complex? I'm going to draw an edge between two vertices whenever two of these balls intersect. And then I'm going to draw a triangle or two simplex if three of the balls intersect. And I'll draw a tetrahedron or when four of these balls intersect. So pretty much, I'm just going to look at how many balls intersect. And this epsilon here is pretty much going to be the radius of the ball. So I can vary the radius of the ball to whatever I want. And I'm going to study this complex that arises out of varying this parameter here. And these are the complexes that arise. So the two common ones that people use in what we call applied topology are the check complex, which is what I was describing to you, and the Vietoris-Rips complex, which is slightly different than the check complex in that you only look at pairwise intersections. So for the check complex, you look at how many balls actually intersect. And for the Vietoris-Rips one, you only look at pairwise intersections. So you want three pairwise intersections to form a triangle. Where here, for the check complex, you want three actual intersections for a triangle. So Vietoris-Rips is slightly easier to check because you only need to check pairwise intersections, whereas check complex, you need to check if 10 balls intersect at once instead of just checking pairs. But the one that we're going to use in this talk is the check complex. And what do we do once we form this complex? Well, we count the number of holes. What do I mean by that? I mean that at every epsilon, so as I vary the size of the balls, as the radius of the balls increases, I'm going to check how many holes there are at each step. So for example, look at this figure right here. H0 means how many connected components are there. So there's 1 point here, 1 point here, this kind of tree here, this line segment here. So therefore, 5, 6, 7, 8, 9, 10. Okay, so those are the 10 components there. I hope this figure is right. Okay, maybe it's not. Okay, well, so the main thing is that you can check how many, zero-dimensional holes, one-dimensional holes. So one-dimensional hole here is something that's kind of like a circle almost. So there are two of these holes at this picture here. And those correspond to these two things, two balls. And as you increase the radius of the balls so that you form more geometry, you get more holes. So in this step here, there are 3 holes. So there are 3 circles here. 1, 2, 3. And that corresponds to these 3 bars here. And so on and so forth. As you increase the radius of the balls, then this figure slowly gets filled. And at the end, when all the balls intersect, you just get one connected component, and that's it. So the point is that we're going to try and study the holes that are sort of significant. And we'll kind of tell you, or I'll kind of tell you what the significant holes are. So the general pipeline is you start with something you don't know anything about. Then you take a sample. So basically take some discrete points. So just take some points. You form the simplicial complex, and then you count the holes. And that's what we're going to do for this cops and robbers problem. We'll start with a space we take our security guards, we form a subspatial complex based on what the security guards can see, and then we're going to count the number of holes in the space that arises. So that's our strategy. And you can apply this to many different things. So data really, you can do some data analysis in general. And what these holes mean differs based on what data you're working with. Like, for example, you can find a hole in like housing prices, or you can look at like cancer data or COVID data because we're in a pandemic. So you can try and group properties together based on these holes. So for example, if you have a bunch of like COVID patients from like somewhere in like Central California, then you can try and cluster. You can find like a connected component of like COVID cases based on their H0. So the connected component, for example. So people are using this to study data. Basically, they're counting holes and they're trying to see what do those holes mean in terms of the data. So that's the applied aspect, if some of you are interested in this. For example, people use this in machine learning. So machine learning is a very hot topic right now. So AI and machine learning. And a lot of things right now, people just gather a lot of data and create these AI to do things. Like if you play video games, there are these AI that you face. Some of them kind of suck, but some of them are really good and they can be professional players. And they're trying to do some sort of prediction based on the data. So if you play like Dota 2, there was this OpenAI, or if you look at all these things like Stockfish or AlphaGo for chess and Go, you can try and make AI like that. Yeah, so let's see. Is it also possible to analyze this problem where some vertices would have a circle smaller? Yeah, so that ARPIT has a very good point. So the radii does not have to be consistent. So you can have some balls that are smaller and some balls that are bigger. That's beyond the scope of this talk, but people are doing research in that area. That's a very good point. You can definitely take different radii around each of these points. So what that means is up to the, well, depends on the data set. So that's a very good point. That's a good question. It does not have to be consistent. So we've described the preliminaries necessary to kind of tackle this problem now. So the first thing I need to tell you about is a fiber-wise space. So this is a cylinder right here. And what a fiber-wise space is something that captures what a space looks like at certain points in time. So every slice of the cylinder, so pretend like you have a knife and you're just gonna slice through a cake. So every slice you look at is gonna be a snapshot of what the area looks like at a certain time. So here I is typically the time interval 0, 1. So I guess to elaborate a little bit further, like for example, if you're taking a walk and someone takes a picture of you while you're taking a walk, and they take a picture of you 1 second later, then they'll have 2 different images, but those are 2 images that represent different points in time. So that's what the cylinder is. So every slice of the cylinder represents a different point in time. So yeah. So what do we do for this evasion path problem? Well, we let every guard or sensor be a vertex of the check complex. And then we take, like we did before, balls of radius epsilon for whatever epsilon I choose around each sensor. And then I form this simplicial complex for all time t from 0 to 1. So basically, what that means is that this shaded region X is going to be what the guards see. So the cops will be able to see every point in the shaded region for all t at all time from t goes from 0 to 1. And this unshaded part right here, or I call it X complement, XC, is going to be the part that they don't see. So you can imagine that this is pretty much the problem you want to study if you're looking at evasion paths. When can you go through space without being detected, right? So can I remain in this region without crossing into the shaded? Can I remain in the white region without crossing into the shaded region X for all time? And you can imagine that places like the defense agency cares about. So actually people are very interested in this type of research, both from like a robotics and like application perspective too. So the slide just says that if you're in the shaded region, then you're detected. And we say an evasion path exists, or a cop can escape a robber. Sorry, a robber can escape a cop if you can move from one end of the cylinder to the other end without being detected. So you never get into this shaded region. So that's pretty much what I said the last slide too. Mathematically speaking, this is what we call a section. So Simon might have taught you about this in an algebra class. So a section usually gives you some sort of splitting if you have some exact sequence. So I don't know if Simon went that far in your algebra class, but these are things that people study algebraically a lot. So an evasion path is just a section. And if you take Simon's geometry class, you might learn more about this, maybe. Unclear. But these are things that people study a lot mathematically. So let's look at a very simple case of this. So if the sensors don't move, then if I stay in the middle here, I will never get detected. However, these sensors right here cover everything in this, assuming we're just dealing with this region, this triangular region right here. So that's not so interesting because it just says that if I just stay undetected, I remain undetected. Here it just says everything is detected on the right. So we want the sensors to actually move around. So imagine playing a video game and then the guards or the cops, they don't move. And you're just like, okay, I'm just going to avoid them. That's not so interesting, or it's not so challenging. Or maybe you might find it interesting, I don't know. So usually the guards, when you're doing like some sort of stealth mission, they usually move around so that it's a little bit harder and where there's some possibility of you being detected. So you don't have like complete free reign over everything. So the problem that people have been studying recently, so this was Gunnar Carlson and Henry Adams at Stanford when they were at Stanford, is that they studied this problem, the evasion path problem, was if I give you the check complex of a sensor network over all time t, can I determine? Just means that if you have a guide if you have a guide to a level in a video game and you know where that this guard is going to look in a certain direction for 5 seconds, and another guard is going to like walk around in a circle for 10 seconds and then go back to its original position, can you actually determine if I can evade detection? So some video games, you might have to get detected, right? So there might not be a safe path out. So can we use the tools of holes to determine if an evade path exists or not? So how are we going to do this? We're going to study this stacked check complex. So all this means is that I'm just going to look at the check complex at certain time stamps. So for example, at the first square on the left, there's a segment connecting these two circles, and there's a point here on the lower right-hand corner. Move a little bit forward in time, and I have two segments. And a little bit further, I get a triangle. And then all the three balls intersect, and I get this filled-in triangle. So we're going to study this check complex at a bunch of time steps. And that's a pretty good approximation of our space. In particular, it gives us all the important information we need to know to dodge all these guards or all these cops. So yeah, so what did people actually do? This is work of De Silva at Pomona College and Robert Grice at the University of Pennsylvania. They did something that wasn't so interesting, or maybe it is interesting. They just said that if there's a hole, if there's this kind of sheet here, this alpha is this purple sheet, such that it separates the cylinder into two halves, so that's what this theorem really means, then there's no evasion path. So namely, if you start from the left-hand side, you can't get to the right-hand side without passing through this purple sheet. Yeah, so that wasn't so interesting. And here's a representation. The representation is here's the uncovered region is this right here, the white. And there's another white region here. And the sheet is this alpha right here. So if you can imagine, they actually got a $10 million grant to study this. And this was one of the main results that they came up with. So the result might be obvious, but it takes a little bit of effort to actually prove this. So another thing that they were concerned with is that if there's something that goes around in the boundary, there still might not be an evasion path. So what do I mean by that? I mean that if you look at this path here, and I follow the path, I have to go back in time to avoid the covered region or the gray region. So remember, left to right is going forward in time. So if I start from here, I get here, and then at this point here, I want to go back in time to dodge the cops, but I can't do that. But if you kind of recall from our hole definition, this is pretty much a hole, right? So it's a little bit harder to kind of distinguish using topology. So what do people do? Well, they looked at these things called zigzag diagrams. They the important parts of our shape into these like shapes that go embed into a central shape. So what do I mean by that? So on the left-hand side here, there's one hole, and it's pretty much the equivalent of this left-hand side of this cylinder here. And this right oval here, it's pretty much the right-hand side of that cylinder there. And then it also is the left-hand side of this cylinder here, and these three holes are the right-hand side of that cylinder there. So pretty much I can encode this in some sort of zigzag. So these zigzags, they encode the important information of the space we're studying. And what do? We count the holes. So here, in this shape here, this is one of the sort of obvious ones, is that we get this bar that arises. It's this full length hole there. And these smaller bars correspond to these smaller holes that appear later in the time. So again, we form our zigzag. Well, we pretty much look at every slice of time and pick out the important parts of time where our shape actually changes, and we study that. And this is what happens. So on the left-hand side, we have kind of the easy evasion path. Namely, you can just follow this undetected region all the way through. For the central diagram, again, that was the sheet that separated them, or you can't really jump from this top undetected region to the bottom one. And there are two bars here that represent those holes. And lastly, there's this picture right here. So this one is the one that gave Gunnar Carlson and Henry Adams a bit of problem. So actually, this was sort of unresolved in Henry Adams' work when he was at Stanford. So this is the one that was sort of difficult to deal with. So the theorem is, if there is an evasion path, then there's a full-length bar. That's, again, sort of an obvious statement. Namely, I need to be able to go from one end of the cylinder to the other end. So I need to have like a hole to follow. But the thing that made this right-hand side a little bit difficult for Gunnar Carlson and Henry Adams is the other direction. So if there's a full-length bar, does that mean that there's an evasion path? And the answer is no. And this is why this problem is sort of interesting, is that this thing here has a full-length bar represented by this blue circle, but there's no evasion path because you can't go back in time. So he was unable to resolve this in his PhD thesis, and it's still a question of how do you actually deal with this. So you need a little bit more sophisticated math to deal with this. So yeah, it's a little bit surprising because you're like, huh, if there's a full-length hole, then I'm good to go. But it's not that easy. So the answer to the evasion path problem, or the cops and robbers problem, is that no, you cannot determine if an evasion path exists given this topological information. So why? So I'm going to look at these two kind of check complexes. So on the one on top, I'm going to start in this white region here. I'm going to stay there. I'm going to go in between these two segments that popped up. I'm going to stay here. and I'm going to go down. I'm going to stay in this lower region, and I've escaped. But for the bottom stack check complex, I'm going to stay on the top, stay in the top here, stay on the top, stay on the top. I'm going to try to go down, but these 2 points here, they just moved up. So I'm pushed upward and I get detected. So these topologically are the same. But these are the 2 kind of spaces that they represent. Namely, the top one right here where you can escape is this right here. The one on the right gives you the bottom one where you are detected because you can't go back in time. So this means that there's some dependence on embedding. And I guess one of you mentioned in the chat about like knot theory. Well, what is knot theory? Well, knot theory is pretty much studying embedding of the circle into Euclidean space. So pretty much the reason that knot theory is interesting is because the embeddings of the circle is kind of an interesting question, or it's not so obvious how to distinguish embeddings. And I think some of you started talking about complements, and yes, people do study complements. So there's this thing called Alexander duality, where people look at the complements of a sphere and study the holes that arise there. So this is called cohomology, if you're interested. And holes are what we call something that is stable. So what we really want to deal with here is something called unstable homotopy. So this is more advanced stuff, and people spend years studying this type of stuff. So it's not so trivial. It's not as simple as here's a hole, the hole exists for the whole time, I have an evasion path. It's a little bit more subtle than that. So we want to find out when does the topological information give us information about the evasion path. So these embeddings tell us when there's not an evasion path. And how does this work? For those of you who have taken calculus, you probably learned about Taylor series, but you can do Taylor series for more abstract functions. In particular, you get things called infinite loop spaces or suspension spectra that maybe Simon will tell you about if you do some sort of project on that. So that's work that is currently being done on this. And it requires some pretty heavy machinery to do. So people are studying kind of like the x squared term for these more abstract functions. And that's going to tell us about if there's an evasion path or not. And what are other people doing? Well, there's something called sheaf cohomology that maybe Simon also has mentioned, where you kind of glue things together and you work with things, you kind of count holes in a more special way. People are doing Morse theory, which Simon also might mention in his differential geometry class, where you get a function and you take the derivative of a function and you look at the critical values of it. So that's maybe if you've taken calculus, you already did this for optimization, but you can do this for things like these tori or spheres or more abstract spaces. So this is the idea of Morse theory. And then Henry Adams and Gunnar Carlson also worked on kind of looking at how things are ordered. So basically, to avoid that problem of embeddings, they pretty much kept track of some ordering that separated the two spaces or distinguished the two spaces. And of course, people are working in robotics too, and computer science, but I'm not as familiar with the work in computer science and robotics. But you can imagine that's, if you have like a security robot and it's just seeing if, is there someone there who isn't supposed to be there? Like how do you detect that? So you can do work in that area too, but I'm not so familiar with that. Okay, so that is about it. So thanks for your attention, and hopefully you got something out of this talk. And I'll take questions now. Okay, so any questions? Yeah, Tejo? I guess,
When doing the check complex,
yeah.
how is there a 2D hole? You said that there was like a 2D hole in one part of it. I mean, when we go all the way back. So how is there a 2D hole?
So you
For
mean
your example. No, the next slide.
this?
And then, yes, this one, the H2 thing.
Yeah, so the 2D hole is the inside.
I think it's like the octahedron kind of thing over there.
Yeah. So it's supposed to be the so here, this is like the one-dimensional hole, but like you can think about like the inside. Like think about like a cylinder, and it's like the inside of the cylinder there. That's the two-dimensional.
I think that it's the inside of the octahedron, somewhere near the upper right, that turns into a case.
Yeah, exactly. So that's pretty much like the inside of the cylinder there. Exactly. A good question. Yeah. Other questions? Yes, Teo, are you still okay? Or Brian? Yeah.
Oh, I asked this in the private messages, and I'm not sure. I wanted to ask if you had any so I saw you later. You mentioned this kind of idea where you could talk about topology in terms of category theory. I was wondering if you had maybe a book that you could recommend on this topic. Maybe one that I could read in the future.
Yeah, so there are a lot of references on the categorical aspects of topology. So the one that most people use is something called Categories for the Working Mathematician. So maybe I can direct message it to you. But a lot of people just read an algebraic topology book, and there are categorical terms that just come up there. Yeah, so the book by McLean. So that's the most famous one. So that's something that I've used before, but it's not the only one. So there are a lot of references to category theory. So when I first learned category theory, it was through Hatcher's algebraic topology, where he has this small section on basic category theory, and it teaches you a lot that you need to know, and then you just sort of pick up terms as you go, because most places don't actually have a course in category theory, even though there could be a course in category theory. So I don't know of actually any university that has a category theory course. But basically, if you go far enough into algebraic topology, it actually just is category theory. So everything that people, maybe Simon has told you a little bit about what an infinity category is or not, but things that people are working on that they call algebraic topology is pretty much category theory. So you'll if you keep going down this route, you'll hit all the necessary category theory things you need. Yeah, and let's see. I don't know who that is, but there's a large A.
Oh, that's me.
Okay, AJ.
It's AJ.
Yeah. Okay. Hi.
I think.
Yeah.
Could we go back to the alpha sheet slide?
Yeah. Yeah, this one.
Yeah.
Or this one.
Yeah.
Yeah.
I wasn't sure what how the theorem related to the
geometry. Yeah. Okay.
Like, what does it mean for alpha to be in the homology?
Yeah. So that,
or how do we know that the boundary isn't zero? Like, what's the relationship between the boundary?
So the boundary not being zero just means that it wraps all the way around the cylinder. So basically, if the boundary is zero, then it doesn't have to go all the way around the cylinder. So basically, by stipulating that the boundary is not zero, I'm guaranteeing that the sheet covers everything from the bottom of the cylinder to the top of the cylinder. So that's what that statement means. So, and this alpha being here means that pretty much it's kind of this type of special type of hole that separates the two sides of the cylinder. So this is called a relative homology. So I'm not going to, or maybe Simon will tell you more about that in an algebraic topology class, but you pretty much do some identifications with everything in this boundary in terms of counting or describing what a hole actually is. But it'll take a little bit of time to actually explain this. So I thought that I would just give you kind of this intuitive explanation here, if that sort of answers your question.
Thank you, that helps.
Yeah. Okay, Teha? Yeah, you have another question? Or maybe not, okay. Or maybe yes. Or Teo, I can't hear you if you're talking. Okay, well, yeah, all right. Well, I hope that was, I don't see any more questions. So thanks for your attention, and those are very good questions. So you'll probably, if you're interested, there are a lot of things that someone like Simon can tell you more about. So I guarantee that every concept here has you can spend months studying and not go so far. So you can definitely work through these in more detail if you really want to. But it's a glimpse of what some people are doing at the university level for research.
Yeah, so thanks a lot. That was a really interesting talk. Yeah, so I'll post the recording of it once it's done. And yeah, so everyone feel free to stick around and chat if you'd like. Otherwise, I guess I'll see you in class next week or sometime. So thanks for coming.
Thanks.